In this demo, we'll go over loading the data we downloaded from the DOT site into R, exploring that data to see what sort of information the DOT has provided, and cleaning the data of extraneous fields that might cause us difficulties in utilizing the data. Prior to beginning this demo, I unzipped the file we downloaded and extracted the CSV file created by the DOT website. This is the RStudio environment. On the left side, we have the command line interpreter. On the right side, we have an environment window which will show in real time the values of our various data structures. Both R and RStudio are available for most operating systems. R is free to use, and RStudio comes in both free and commercial versions. Throughout this course, we'll be using the free version of RStudio. Now let's start by loading the data from the CSV file. We will load the data into an R data frame with columns and rows. We specify the file path, separator, whether the file's first row is column names, and how to treat strings. You may have also noticed how R uses the less than and line symbols to indicate assignment. R also supports the equal sign for assignment, but most R programmers prefer to use the less than and line for assignment. Now that we have the data frame loaded, let's see how many rows we have. We use the nRow function to get the number of rows in the data frame. Wow, that's a lot of rows to process and it's really going to slow us down. To speed things up, let's restrict data to flights only between certain large airports. We do this by creating an R vector, a list, containing the airport three-letter codes. Now we use a subset function to get the data for only the flights between these airports. As we see, subset is doing a select operation. Let's check the number of rows again. Now we are down to a more manageable number of rows. Remember the rule, data will never be in the format that you need? This is true even with very clean data sources like our DOT data. As it is now, there is data that needs to be removed, altered, or created to make it work for our needs. Let's visually inspect the data to find any obvious errors. We'll use the head command to look at the first two rows. As we can see, we have a lot of columns. Most are as expected, but notice the last column named X with the values of NA. That's suspicious. The data exported from the DOT site did not contain an X column. The X column was created as part of importing the CSV, and the NA means the data was not available. It looks like that column can be dropped. But to be sure, let's check the end of the data frame with the tail function. It definitely appears that the X column has no value, so let's remove this column. In R, a column can be removed by setting its value to null. Let's check the data again. Good, the X column is now gone. In general, we want to eliminate any columns that we do not need. In particular, we want to eliminate columns that don't have any values or are full of NA values. But we also want to eliminate columns that are duplicates or provide the same information in a different format. We could visually inspect columns to see if they are really the same, but visual inspection is error-prone and does not deal with the critical issue of correlated columns. Correlated columns state the same information in different ways, such as an ID and the text value for the ID. These correlated columns do not add information about how the data causes changes in the results. Worse, they can amplify a bias because some algorithms naively treat every column as being independent and just as important. For example, imagine what would happen if we predicted house prices and the size of the house was in both square feet and square meters. Size would result in being twice as important as it should. Let's look at some data and see if we can locate some possibly correlated fields. In looking at the data, Origin Airport Sequence ID and Origin Airport seem to change together, as does Destination Sequence ID and Destination Airport ID. I'm not sure if we use these fields, but if they are correlated, we only need one from each pair. We can verify the correlation of values using the core function. The closer the values returned to are to 1, the more correlated. Wow, a perfect 1. So Origin Airport Sequence ID and Origin Airport ID are moving in lockstep. Now let's check Destination Sequence ID and Destination Airport ID. Another perfect 1. So Destination Airport Sequence ID and Destination Airport ID are moving in lockstep. Let's drop the columns Origin Airport Sequence ID and Destination Airport Sequence ID since they are not providing any new information. Using the core function works for checking correlation with numeric columns, but it will not work with string columns. I'm pretty sure I saw some potential duplicate string values. Let's check the data. Notice that unique carrier and carrier also look related. Actually, they look identical. We can see if they're identical by filtering the rows to those where unique carrier and carrier are different. R makes this easy. No loops to write. All the iteration is done for us. We enter the row filter criteria and get a list of all the rows where carrier is not equal to unique carrier. Notice the comma right before the closing brace. R can filter a data frame based on a list of rows and a list of columns. The comma separates the filter for the list of rows from the filter for the list of columns. Since we only want to filter by row values, putting a comma with nothing following tells R to filter only by rows. Now we can check the number of mismatch rows within row. The zero mismatch means that carrier and unique carrier are the same for all rows, so let's drop unique carrier. Let's see what the data frame looks like now. Looks like we have cleaned up the data frame pretty well. Now we can move on to more advanced changes to the data.